I think basically I'm saying what I'm going to say is basically Hamiltonian system, but start from the scratching. So suppose H, I and Pi is a Hamiltonian. Okay. Now, you know this is it is defined on a configuration space Q. So on Q, configuration space. So now you know that's a dH, the particle is moving not in a Q, but it's T star Q, but particle is moving on T. I will tell you what is this. So Qi is a particle moves on some space. That space is called, you call it a configuration space. This particle moves on some kind of space, it may be R2, R3, R4, N4, but these are the space. And you know these things, if you take Q, then you know there is a tangent bundle you can define, but that means at each and every point I can define a tangent space. I need all these things because you see, listen. Then you have a union of all these points together. Then you have a bundle structure. So that's, you get a bundle structure, TQ. Now, similarly, I can define the cotangent space also. And in phase space are typically cotangent bundle space. Basically, all the spaces are cotangent spaces. Now, you don't have to know. Say, for example, I don't know where is the duster. Okay. So let's see if I do this Qi, Pi, then del H, del Qi, dQi plus del H, del Pi, dPi. This is one thing you know. And you have to know another thing, it's called a vector field. Del Qi, I and del H, del Pi. You don't have to know much. These are the things, two things starting. First thing is actually giving out second thing is giving out the equation, some motion. Is it okay? Because you see that if you, this is your favorite J, this is grad H, and if you take into account the Qi dot and Py dot, suppose Pi dot, so this is basically the equations. So the right hand side, you were saying the vector field. Now vector field is basically, so this satisfies some equations of motions, as you know. This is called the equations of motion. Is it okay? See, I pulled my hand a few days ago, a muscle pull, so it's a big problem. So now this is a equations of motion. And how you interpret these things? Qi, P are the integral curves of the solution of this equation. Are the integral curves. So that's the trajectory, by all means. Is okay? Good. And then what happened? XH is the infinitesimal vector field. Trajectories, infinitesimal vector field. So it's okay? Now, I can write down, in fact, this thing I can write it down in terms of a operator language also. And this is actually del H, del Qi, del Pi, minus I plus del H, del Pi, del Qi. So you can see this thing matches, because if you see in my operator, if I say it's Qi dot, so you can see that this is the only del H del Pi, because this is independent coordinate, that will not work. So del H del Pi. So this is your Qi dot. And then another one is basically Pi minus del H del Qi, Pi dot. So these two matches quite nicely. So one is I'm writing in terms of your, that's why you, in all practical purposes, this was also, we call it a vector field, the whole thing, and this is obviously in the operator forms. Why I'm saying this thing? See, these are conservative systems, and conservative systems has some kind of interesting feature. This thing I can able to write, for example, and I can also write pi comma h. You know these things is a Poisson bracket, and Poisson bracket with respect to what you call it a, so if you f and g, so is equal to del f del qi, del g del pi minus opposite side. That means del h del f del pi and del h del qi. All the whole business of the Poisson, this whole world is very interesting because they have some kind of similar structure. And one of the very, all phase space, all space in the world carry one structure. And that is universal structure. That is something, you call it it's a one form, let me check my notation here. Irrespective of any Hamiltonian system you carry, this is the structure it carries. This is a two form, it's basically wedging over this one, it's a two form. And how the dynamics, universal the way of writing the dynamics is basically IXH omega. If you contract it, it gives rise to H. You know H, so given H, I can define or I can derive XH. And XH means equations of motion. This is clear. That's the routine tasks I'm going to do. Okay. Not only that, so this is, if you understand this point, then there is an important thing also that let me do this thing, because if you feel uncomfortable, as you see, this is a contraction. XH is that. So let us write down in my own forms del H, del Qi, del Pi minus del H, del Pi, del Qi, and then you have this omega. This is I. This is my I symbol. Its omega is dQi dPi. Now, if you want to contract, for example, well, I have taken it wrong. See, then this is because this is antisymmetric, or skew symmetric. So if you change this one, it dPi and dQi. So this thing and this thing comes together. So this gives rise to minus del H, del Qi, minus del H, del Pi, then del Qi, dQi, dPi, dQi, dPi. And this is actually called minus d of H. Sorry, I actually taken some different convention, otherwise it's. So this is the way. Another thing is that, just one more thing that I want to is say, IXH, this is an operator. This is a very fine operator which is called a Lie derivative with respect to vector field. So all practical purposes you will say this you will zero for conservative systems. That means it is a geometric definition of your Liouville's theorem. Liouville's theorem. That means the preservation of the volume. That's the definition. Now, you know this is the equations of motion. Suppose I give you another system of equation which is like that. And Pi dot is equal to minus del H del Qi minus alpha Pi. Clearly, this equation shows you this is not a conservative system. Is it okay? Because you see that this animal is sitting here, it is actually frictional or Rayleigh friction type of things if you take into account the original Hamiltonian. So this is the equation if you get, then how will you tackle these things in that form? Step by step I'm going up. The complication is there, that when you start doing this type of thing, you cannot able to do it in a conservative, because it's a non-conservative thing. The important thing is that you tackle with this problem, which is what you call it a contact geometry. See, these things are always there. How the contact geometry is very important, because understanding thermodynamics, in the language of first law, second law derivation rigorously, you need a contact geometry. So let me explain you a very simple way, and I think it will be okay for you, because I don't want to go into the jugglery anything, but how to use this thing, that is an important one. Because the most important thing is that from this set of, using this set of geometry or the mechanics, you would able to derive certain thermostat problems, Nusse-Huber type of thing. Which is, so let's start in this case, suppose eta is a one form. And you know, all contact manifolds are 2n plus 1 dimensional. Contact manifolds are 2n dimensional. So this is a volume form, which is of course not equal to 0. Now what happened? Say there is exactly one vector field exists. So there exists a unique vector field xi. That means del del x or something type of things. That's the contact manifold has a contact structure. This is a contact structure, and this is this. So this is a one form, contact form, and this is a volume form, total. So there exists a vector field xi. So that vector field xi follows this one. This is the uniqueness, and d eta when xi comma dot will be 0. So d eta is a 2 form, but when you contact with xi, will be 0. So this is enough to give you the construct of xi, because I want to construct xi. Once I get the xi, that means I can able to write down the equations of motion. So that's what I have to find it out. And in fact, what are the important equations? All time-dependent Hamiltonian systems, thermostat problems, and many other systems are all actually coming from this kind of construction. So it's the first thing that you encounter when you have a non-conservative force. Okay, so if you do this thing, so you need two things. First of all, LXH, I need some kind of, suppose H be a function which corresponding to that, I can have a vector field. Now if I have eta, I can use those Cartan's magic formula, which I wrote for this one. I can do this thing. Then you get something like IXH d eta plus d of IXH eta. So this will be, so d eta xh, and then the next one will be completely d of eta xh. This one, and there exists H. How H is defined? H is defined from this contact form. So it's one form, it's a vector field. So if you take a contraction, you get a function. This function is H. And this is exactly what it. Now, how will you derive those equations of motion? The equations of motion, you will derive. See, I need a, what is Qi, Pi? Here, in this language, say for example, these are called Darboux coordinates. Okay? Now, if we do this thing, Darboux coordinates, here also we have a Darboux coordinate, because from one dimension, this S is coming, and 2n is basically Qi and Pi. So I runs to 1 to n. So these are the 2n now plus 1 coordinates. Now, okay, so there is a nice piece of things is there. So if you have a contact, this is a contact manifold, then you know this is a tangent bundle, and because of this, and what are the vectors you have? One of del del xi is very important for me. This vector field is Reeb vector field, is very important for me, and with using this vector field, I can decompose. This is the vertical one, which is the del del xi, and the horizontal distribution. So how is D is defined? D is basically living kernel of eta. So you see, I can show you with a second calculation that these things do not go too far. So this is a xi, and I have a Pi, big, and Qi dot. These three vector fields, two from here, one, I mean two in one vector fields. So this to exist is del del S. Eta already I defined. Okay, eta is basically I defined in the following way. Then of course Pi dqi, I believe so. Eta I defined in this way. Yes, fine, no problem. Then what happened? dds, and then there is a del del Pi, and Pi del del x minus del del Qi. So if you do this thing, you can see it is fine eta, because dds s is 1, and rest, if you look at these things, contract with these things, this is 0. So it is sitting in the null. If you do this one, so Pi del del s minus del Qi, if you do, then you look at dds plus Pi dqi. The first thing is that you get a contraction here, we get a Pi, because you remember dd1. Second one, you do that is minus Pi, so this is 0. So it is also living in the kernel. Kernel of eta, kernel of eta. Now you look at if you look at the algebra sides of this one, you will get a very nice expression. And this expression is given by pi dot qi dot is equal to delta ij xi, and xi pi dot is equal to 0, xi qi dot is equal to 0. Of course, this algebra you always see in your life is called Heisenberg algebra. Heisenberg algebra. Okay, now what you get? So, if you use these things, then I can define that xh satisfying all the conditions. This xh looks like this one. You know the xh here, but now you will see the xh in the contact form. So this is xh is equal to h pi del h del pi del s plus pi del h del s minus del h del qi del pi and plus del h del pi del qi. Now it's equations of motion. Why it is equations of motion? Because as you say, what is s dot? S dot will be just like xh s. So h minus pi del h del pi. Second one is actually your pi dot. So pi dot is equal to minus pi times del h del s minus del h del qi. And then the last one is qi dot, which is nothing but del h del pi. So this is a set of equations. And now you can see, you can able to write, because if you have some kind of other things, h is s dependent and pi automatically this is coming. So what I wrote it down few minutes ago, that this one, you recovered this is, and you recovered another one which is s, but it is basically nothing but action principle. Why action principle? H minus pi qi dot, which is nothing but L. So s dot is equal to L means s is equal to L dt integration. So that's the action principle, Hamilton principle, nothing more than that for the ordinary case. Other cases actually it gives rise to a thermostat problem. So this is the first thing that you come across with a. So this is that the first come across this time dependent system, and this is a Hamiltonian, purely Hamiltonian. It's using the contact geometry, nothing more than that. And this contact geometry, the whole part was actually long time ago. There was a standard books are written in Arnold book. So, but nobody cares about these days. So they don't care. But this is the whole structure. Now from here, once you know these things, like here also, we can do the generalization. In this case also, we can do a lot of generalization. I don't want to do that. I just want to show you another example, which is very important. You see how these things give you equation, this whole set. Another one, if suppose I told you this is my phase space. Now suppose it's 2n already. If I multiply with r, that means it's a time dependent Hamiltonian space. So that means you can define a Hamiltonian qi, pi and t. This is T, which belongs to R. Qi and Pi, these are belongs to these two sets, Q and the cotangent space. Q belongs to called Qi's, and the fiber coordinates are Pi's. Okay. Now, what will happen if I have two projections? This is one, and other also I can do some kind of this projection is R. So this is always this is basically a vector bundle, which is basically trivial vector bundle, nothing more than that. So you know pretty well that in this case, like omega dqi which dpi, here also we have a standard one form, and this actually d of theta is basically qi pi dpi. So I could redefine the whole things pi dqi minus h dt. This is called Poincare-Cartan form, one form. Then d theta h is actually dpi which dqi minus dh which dt. We have again one form which is equal dt and theta h, d theta h. Now what happened, you know, this is our favorite reef form, eta. Immediately what we do, what you get, this is my eta, and in that case, I psi dt is equal to 1, and I psi d theta h is equal to 0. This was the condition. Using this condition, you can find only one unique value, that is del t plus del h del pi del qi minus sum again del h del qi del pi. So this is again, you know, this is equations. This is basically, this is Reef vector field. It will give you the equations because that's all. How? Because this is what you know, that qi dot is equal to del h del pi, pi dot is equal to minus a del h del qi, and ti dot is equal to 1. Because t is no longer independent coordinate, so this is the set of equation for the time dependent. So this is the setting that exactly works for all these cases. Now question is that still all these things are not important or cannot control how to write equations of motions for, you know, Barger equations, Cahn-Hilliard, or many other things, where we have two parts. We have a part is one hand is a you know, symplectic part, that means like Poisson part, and other is a diffusion part. And that's the reason actually people study metriplectic structure. So let us do a very elementary example, because the whole thing was much more complicated in a sense. Already you are going to see that I didn't go to metriplectic, but before that you almost closed your eye that these are the things, but this is the procedure that people proceeded year after year to move from this direction to what they call metriplectic geometry. And Amit's supervisor was world famous for this because he was formulated those things carefully, adapted this thing. These days, of course, now things have become much more important because there was a there was a thing called generic, which I will tell you the name, I think. It's called a general equation for non-equilibrium reversible and irreversible coupling, where these whole things you can able to generalize, even with the stochastic terms. And you know, Langevin equation, stochastic Langevin equation, Fokker-Planck equation, many other things can be brought into this generalized framework or generalized Hamiltonian framework. So what is this metriplectic? The metriplectic, in a very simple language, suppose, let me start with a very, because you need all these things. See, suppose I have a qi dot, qi h, and then you have a diq. This is what you call a dissipation term. Previously, what you do, q dot. So for a simple-minded q dot, you can able to take care of this thing with a contact geometry. But if you have a nasty qi dot, you cannot able to do these things in a possible way. So there were two pieces of objects. You can see, it's a pasting two things. Kitne bhai? Oh, then 2 minutes. Okay, 5 minutes max. Bargain. So this is, then let me say this thing. What is the spirit? Because the spirit was there that you can able to do partly the old symplectic part in this way, and the next one is this way. So let me give you one example, because for example, let's do some PDE. And it's difficult. Suppose this is your PDE, and F and G is defined as del F is a O operator, del G del U dx with some volume from moment. If you take into account your O is skew operator del del, then what I can write it down, this part is simply ut is equal to 3u ux. Then du is another operator, which I defined in this form. It's basically this bracket is. So I can define, for example, f comma g, which is a omega del f del u Laplacian del g del u. If you do this simple calculation with u and h, you call it a u and h symmetric, it will give rise to uxx. That's your Berger equation. Now, how you generalize these things? I think I don't want to see in a basically another example. Maybe this is the last example. Say for example, you need 2D Euler equation. 2D Euler or even Rossby, they all satisfy the same kind of things with some kind of transformation. So u dot is omega dot is omega del h del omega, and this is fine. But if you have this one, how will you do that? This part is a symplectic part because it's basically Poisson part. But this part, when you try to do that, you have to do this dissipation factor extra. So similarly, in many quasi-geocentric. Now the question is that there were these brackets. What we have used here is a simple-minded bracket. It's all on Rn or something. But because it's a infinite dimensional or group manifold, or even if you want to do your rigid body dynamics or anything, these brackets will not be the normal those brackets. These are basically Lee-Poisson brackets. What Professor Morrison always started from his life, it was actually these brackets were he defined from a very different way, and this is called non-canonical Poisson bracket he started. Those Poisson brackets turned out to be all Lee-Poisson bracket structure. So I think the whole idea is that I can say you that, and the whole, so I should now stop here, but this is a completely different ball game. And it is not a standard just doing the work and this thing. There are considerable amount of things are involved in it. And while sitting here, I did some work on his surface QG type of things, surface QG, which turns out to be geodesic flow of a fractional Sobolev norm on an area preserving group. So that's my result, but I can't share with you in full-fledged way, honestly speaking, because it has encountered hugely maths. I stop here. Sorry for the, but if you have any questions, I can informally discuss with you, but it is a richer area because Hamiltonian area, and it has a lot of people say he's a supervisor, actually one of the top boss in this whole. When I asked Jean-Luc that why are you not doing your Hamiltonian theory, he said my supervisor killed us, he killed me because he has some other collaborator, Tassi, Materesi, all these people. That's but this is you can do fluid dynamics in many ways. I do fluid dynamics from the Hamiltonian point of view. Okay. Okay? Thank you. Has it gone anything in your head? No. Yes, because I thought yeah. Yes.